engineering and manufacturing needs. But when you start looking at mid to high volume manufacturing, it's typically too slow, and that drives most manufacturers, particularly more consumer and automotive type of manufacturers, to go to tooled solutions and use traditional manufacturing approaches, just because tooled manufacturing solutions can basically build parts in seconds or minutes. And typically, a lot of the additive processes build parts in hours or day as far as unit of measure. And so it's just too slow for doing anything for any type of serious type of production. So with that in mind, for those that are on the webinar that might have stopped by an Impossible Object booth over the years, this is kind of a real example that most people can relate to. This is basically a miniature wave solder pallet used for circuit board assemblies. This part that you see on the chart and me holding in my hand was printed in 15 seconds. Now that was the print time. There's heating and pressing time behind that, and I'm going to give you some values on that. But just to show that, hey, you can print these parts in 15 seconds, the important point here is we're really trying to take a bite out of lowering the cost and doing new product introductions at a cost-effective way that challenges traditional manufacturing techniques. Now, with that, this CBAM technology is really designed for speed. Not only speed, and you can see on the right side here, compared to other additive processes, as far as the various powder bed, extrusion-based processes out there, the CBAM 25, which stands for 25 feet per minute as far as deposition time, we're doing basically 3,125 cubic inches of material an hour versus like laser sintering, great technology, 191, so significantly faster. But again, the whole intent here is to really go after more of the traditional manufacturing approaches to take a bite out of that with this type of composite technology process. So what you see here is what we call the CBAM 25 machine. This is what we are launching at Rapid in June, and the machine will be live at the Rapid Trade Show in Los Angeles. But this technology is a technology that was invented by Impossible Objects. We have over 30 granted patents. And it's really an industrial grade technology building on 2D printing technologies that you're going to see here shortly. So before I get into how it has its roots in 2D printing technologies, I just wanted to maybe kind of level set with the audience and say, some of you might be familiar with how this process works. It's a 3-step process, and it's basically print your fiber substrate preforms with your matrix material on it, like I'm holding up in my hand here. Then basically you're going to take these stack of composite preforms, so you're going to heat and press them. That's where you're forming your part. Personally, I like to think of it as kind of tubeless compression molding. And then you're going to remove your composite parts out of a build block, and I'll talk to this here shortly, but it's a 3-step process. And I'm going to play an animation that kind of is going to walk you through this process.
Imagine producing complex carbon fiber and other composite parts at production speeds and volumes. Impossible Objects announces the world's fastest 3D printer. The CBAM 25 produces strong, lightweight 3D composite parts that are printed up to 15 times faster and available in a wider selection of materials than conventional 3D printing. Here's how it works. The process starts with a CAD model of the part. The model is sliced into thin layers and prepared for printing. The machine starts with a web of fiber substrate. Printing at an astonishing 25 feet per minute, the image of each layer is printed with an aqueous fluid onto the web. The web passes through a powdering system where polymer powder is flooded onto the web. The powder sticks to the web where the fluid is deposited. The excess powder is vacuumed off, and the polymer is selectively deposited on the web. Microscopically, you can see polymer particles penetrating the fiber web. The machine prints continuously, cutting the web into individual sheets. The sheets are then stacked to complete the entire printed geometry. The final stack is compressed and heated to the melting point of the polymer. The particles melt and encase the fibers to fuse the sheets together into a solid part. The fused build block moves into the automated sandblasting unit. The uncoated fibers are removed, revealing the finished parts. At an incredible production rate of 25 feet per minute, the CBAM 25 is the fastest 3D printer in the world, capable of producing stronger, better, and lighter parts.
So what I was going to show all of you folks, if you can see the video here, I'm holding up a carbon fiber substrate here. This is considered to be a non-woven surfacing veil. The fiber lengths are between 15 to 25 millimeters with a random dispersion. Come from a number of major material companies worldwide, but they're making it to our specification here. This is about a 24 GSM weight fiber substrate here. And you can see on this, there's basically, we deposit an ink onto this fiber substrate, and then it gets flooded with a 50 micron thermoplastic powder. And the ink basically, it's not an adhesive, it's not a resin, it's basically kind of a slow evaporating water for an easy description here, but it's holding the powder in place. And this deposition, the printing, and the powdering is all done at room temperature, and recycling all the powder that comes off this fiber sheet for future build. So there's minimal to no loss of expensive thermoplastic powder, particularly like thermoplastics like PEEK. PEEK is a very expensive material, regardless of what kind of feedstock it comes in. And so what I was also going to show you here is that these fibers have about an 8 micron diameter, and you can kind of rip them easily just with tension. And so that when you basically go to stack these, I should back up here a second. So when we print this sheet, we're doing it with 1200 dots per inch piezoelectric print heads. And when we actually print a sheet, we actually didn't have a vision system in the machine that's looking at, hey, is the printed area correct compared to the layer from the CAD file, and doing that in situ check really quick. And if not, we can purge it and reprint it. So build recovery is absolutely incredible there. So then when we actually go to powder it and we come out of the powdering station, we have another camera looking at, do we have the right powder load? And because powder load is very important, because if you get not enough powder on, you're going to have low material properties. If you get too much powder onto your printed region, you're going to get squeeze out, and that's going to impact your dimensional accuracies. And so we have another inspection point there looking at, is powder loading correct? Third and final, then you're going to see this in the next video when we actually go stack these fiber preforms into a press jig, making sure that they are properly registered into that press jig, and stacking all these fiber sheets up. And then we actually have a camera looking at edge alignment, so making sure a sheet's not sticking out to the left or the right type of thing, because that will then impact mechanical properties and strength properties. So 3 inspection points in the whole printing process, and great build recovery should you lose power in the building, should you have a mechanical failure and component in the machine, which is very nice. So I just wanted to kind of highlight that. So that's the animation. That explains it's a 3-step process. So the next thing I'm going to show you here is, this is the engineering prototype machine that has been built, and Impossible Objects has 2 locations. We have a location, our headquarters in Chicago, Northbrook, Illinois, a suburb of Chicago. And then we have our Rochester, New York facility. And with the Rochester, to give you a little history there, our current CEO, Steve Hoover, was the former CTO of Xerox, came on board about 2 years ago. He went out and hired a bunch of his tenured design engineers that was doing 2D printing systems. And this is the machine that's been running for 2 years. We're making parts on it, but you're going to see its whole base background design build modularity approach coming out of 2D printing here. And just the whole purpose of this is to let you see this machine. It is real. It's been building parts for about 2 years and how it works. So without further ado, and this does not have voiceover, so you're going to unfortunately have to listen to me. So basically, you put your roll of fiber substrate on here. This is your pan carbon fiber that's being pulled through. You have your typical, so you have your web steering module here, typically used in 2D printing here, maintaining your alignment and tension on the material as it goes through the machine here. So your third module is basically your print module. This is your piezoelectric print head, 1200 dots per inch, lasts the lifetime of the machine. A vision system in there as well, looking at the printed system. Right here, I'm going to pause it for just a second. If you can see my cursor moving, this is basically, this is the unique aspect of it, is basically, this is your powdering station here. So this is your peak powder in an auger system. 50 micron is a typical particle size here that's being flood coated onto that fiber sheet. It has a printed image on it, so as soon as that powder lands onto it, it's basically a capillary action that's holding that 50 micron powder into place. And then we have the vision system here looking at it. And then right here, this is a vacuum. It's vacuuming off all the loose powder on the dry section of the fiber sheet here. That's the vacuum, and it's going through a cyclone separator, and we're using that for future builds. All done at room temperature. So minimal waste, no thermal effects to the matrix material, and you get away from, like other additive processes, you usually have to heat it up close to the melt point of the material and then push it over with a laser, or with extrusion, you have to get it to its melt point and then push it out. So that's what you see here. That's kind of the advantages of room temperature deposition here. So powder on, powder off, and you can see kind of the images that are sticking to that. And now basically we have an accumulator here. You do not want these printed sheets stopping underneath the print head or the powdering station. So you have an accumulator loop here to prevent that from happening. And that's what you're seeing at this particular module. And kind of at the top of the page here, you'll see an artifact up here with a little white tab that gets picked up by a sensor, and then it gets cut off. It gets cut by a guillotine cutter. And then lastly, and this is real time, doing a printed sheet every 2.2 seconds, it's being then automatically stacked. It's being tapped from the end, tapped from the side, and then being checked with a registration camera to ensure that we have proper sheet registration. So that is basically, and you can see, and it just runs really fast. So we get to speed, we get a lot of material options with the room temperature capability here. People in industries that do bigger parts, the build area of the CBAM 25 will have an 18-inch by 18-inch by 5-inch tall build volume. People say, well, can you do bigger than that? Yeah, we can do bigger than that. But I mean, that's kind of where we're starting right now. And so you have scalability for speed and size and material options is kind of a key. So just again, modular design, a number of reasons behind the modular design here. This is a five-unit modular design. In order to get it into folks' facilities or use elevators to set it up in people's shops. And then in the future, let's just say you wanted to do taller builds and you had a smaller stacker on it. You can basically potentially order a larger stacker in the future and remove that one and bolt on a new one on that front. So a whole lot of thinking future thinking going into modular system design here on this front. Here's the machine that's being launched, and on that front, Impossible Objects, being about a 10-year-old company, is only doing a limited launch of about 6 machines this year. Most of those machines have been sold, and so that we can properly support it. Being a new technology, there's certainly going to be process-related issues, potentially hardware, software-related issues, so we can burn it down with the engineering staff and then get that feedback of what's working and what needs some additional attention to it, being a new technology. So this is what's being released and sold as we speak. And again, it's really built for the manufacturing environment and not as much for a prototyping environment based on its build speed. Getting into some of the material properties, and I'm going to do a deep dive here, but if I've talked to some of you folks in the past, you might have heard this as my spiel, but why do you want to go to composites? Typically, composites is strength in weight. And with the Impossible Objects CBAM process, you get basically similar strength to weight as 6061 aluminum at about half the weight. And for a number of different industries, that's really important. And so that's kind of the general feel for why would you want to go to composites. And by the way, typically composites have been very expensive to manufacture using traditional techniques with a lot of CapEx, a lot of skilled labor, expensive materials that come out of freezers with out time. It's kind of changing the equation and opening up other industries that can actually now use cost-effective composites for weight reduction applications in particular. Material options. One of the things here on the left side here, again, we're working with 2 main fiber substrates, a carbon fiber and fiberglass. Fiberglass is somewhat lower cost than carbon fiber, but it's a little bit heavier. But you do have some options. We have worked with some Kevlar and some other fiber substrates in the past. On the matrix materials, we're basically commercialized on the systems to date. It's been basically the PEEK and the nylon 12, but we're not too far off of offering a nylon 6, and we're not too far off in the coming soon is a thermoset epoxy material. And what I'm holding in my hand here, this is not ready for prime time, but this is now a unidirectional fiber sheet rather than a non-woven random dispersed surfacing veil. And we had to use a thermoset because it had to be low viscosity because these unidirectional fiber sheets are very dense, and we need to have the material flow and wet out these fiber sheets. And the big deal here is that this is 600 megapascal strength property with close to 50% fiber volume content. And it puts us into kind of that first range of doing structural parts made with traditional composite fabrication techniques. So this is basically kind of a look at where we're at with the non-wovens, carbon fiber fiberglass with the 2 matrix materials, either nylon or PEEK. These are all in-plane properties. I will mention that some of you probably are materials engineers or design engineers that want to know, well, what's your out-of-plane properties? Well, out-of-plane properties becomes a function of what your native polymer is. So just look at your strength property, PEEK, for example, with a little bit of knockdown on that, that's going to be your out-of-plane property. But this is your in-plane properties that you see coming off the system today. Far as part accuracies, on the left side there, we did a number of artifacts, and we've done quite a number of the NIST artifacts. I mean, probably hundreds of the NIST artifacts here. But if you look at feature detail compared to more of the installed base additive processes out there, powder bed and extrusion base, you look at the concentricity of holes compared to the CAD design, the CBAM process does pretty good on the left there, as you can see. On the right side of the chart, you'll see feature detail. And a lot of thin walls, we can go to about, there's some factors here, but kind of rule of thumb is we do about around 2 millimeter thickness walls with this process. And, the fidelity of wall thicknesses that can be built with the CBAM process compared to the incumbent. Another thing that I will mention, a typical question that's asked being a new material and process is what's your part accuracy? Well, if we took a customer part and built it as is, we would feel comfortable saying that it's usually within a 400 micron part accuracy on the first part. But if you needed better tolerance than that, we could actually apply a scale factor, do a rebuild, and get close to about 125 micron accuracy. And that's true for a lot of additive processes, but this is the accuracies that you can do for with the CBAM process. So, okay, being a new technology, some of you are thinking, where is it being used and how is it being used, for what types of applications, and what's the use conditions of those applications? And so a lot of work, and I'll do a deeper dive into some of these here in the subsequent slides, but the electronics tooling. Believe it or not, for much of the electronics manufacturing out there, it's really kind of untouched by the most part by the additive processes. And many of the tools used on wave solder lines and reflow lines are typically machined out of a carbon fiber PEEK board. So that's a huge focus area where the technology is really saving time and money for a lot of contract manufacturers out there, and a big emphasis. And it's a lower risk insertion point too for a new technology. Automotive, there's a number of, particularly with tier ones, there's a number of part families that's being looked at for underneath the hood. And as if any of you are on from the automotive industry, the important thing is repeatability and unit cost, unit cost, unit cost, unit cost. And so we think that for some of the material combinations, for the right part families, that's going to be a big area of growth for us in the future. On the defense side, over the years and even continue today, the company does a lot of work. We have quite a number of different Department of Defense grants, kind of taking the technology to the next level. But we did a project that started in 2018 to make non-structural parts for in-service Air Force vehicles. This happened to be a part for a B-1B bomber. It was a hold down latch that was in the cockpit of the B-1B. It was non-structural, but it had to meet FST requirement, flame, smoke, and toxicity requirements in order for that part to get into the cockpit of the vehicle. Bottom left, quite a bit of work that you'll see here shortly in the unmanned systems and air vehicles. And we are also doing some limited work with the air mobility. And air mobility, for those that don't know, is basically flying cars or flying motorcycles. They are coming sooner rather than later. And then the technology is placed in a number of different research institutes. And some of the partners that are actually running the technology happens to be NIAR, National Institute of Aviation Research, so that they can actually build and test and write the reports. And then once those reports are written, those are pretty much like taking the check to the bank with the OEMs that from an organization such as NIAR. So tooling. Okay, we've got a couple different types of tooling families here. Fabrication tooling, you'll see at the top row there, injection molding. Now, it's hard to beat machining, aluminum machining of injection molding tools. That's very pervasive. Supply chains very well established. Hard to beat the cost of that. But if you actually are looking at time compression to validate that your tool design is correct, and or your part coming out of that tool design is correct for new product introductions, we've actually done some injection molding tools for lower melt point plastics. And that's basically for validation of tool design and part design for new product introductions. And just basically compressing schedules there. Hydroforming. So if a lot of sheet metal still being used, and all the forming tools out there. So we've made hydroforming tools And then the same goes true with thermoforming tools. And then the last one that it's basically under development on this last one here, but it's autoclave tools. When you're actually doing your standard composite layups on tools that are then vacuum bagged, and with your call plates and pressure intensifiers put onto that, and then vacuum bagged and put into autoclaves at 350F, 90 psi. And the goal here is to, number one, have a lighter tool, but more importantly, have a tool that has lower thermal coefficients of thermal expansion that has a closer match to your carbon materials coming off of that. So those are some fabrication tools that the technology is being applied to now on the electronic tooling. This is a major focus area where the technology is being used, and we need to show you some quick examples here. So anything that has a printed circuit board assembly and goes down either a wave solder line or a reflow line will need these types of tools. And oh, by the way, we learned that these tools, after so many duty cycles, become consumed and need to be replaced depending on the volume that's going on there, if it's a major production run. And so we're doing a lot of tools for various electronic contract manufacturers, large and small. And we're also doing a lot, I don't know if you can see my camera here, but a lot of the hold down mounts and the different tooling details that go into these are being made as kind of like a kit. So that's a big area. And the reason being is that these tools can see up to 260 degrees C. And on the back side of the tool that they will get solder on there and will have to then be cleaned after so many duty cycles, and they'll go through a chemical wash, and so they have to be chemical resistant as well. And then there's other unique fixtures used in the electronics industry, and these are some examples of different holding fixtures and different heat sinks as it's going down the lines that you don't want to. We've done quite a number of different fixtures for the electronics industry. What you have here is drones and a number of different part families. I mean, the fun thing for us is that we've worked with a lot of great companies and propellers. I mean, depending on your propeller configuration, depends on, you know, what your airspeed is, your altitude is, lift capabilities are, noise emission. And so by just changing your propellers on a Class 1 drone, can change the capability of that particular drone. A lot of different structures, and you can kind of see here on the middle row the different types of part geometries that's been made for drones, and kind of lattice structure and light weighting going on there. You can kind of see the parts I'm holding up here, and then the bottom category is a lot of enclosure cases and different types of instrument panels for drones, as some illustrative examples for you. Again, weight is king for anything that flies, or if it's an unmanned system and it's running off of a battery. The lighter weight, the longer, the more payload or service time it can last. Another typical question, you know, with being a composite thermoplastic, you know, what kind of finishing techniques can you use? And you can CNC machine this. You can put them in media tumblers. You can hand sand it. And so we've applied many of the different post-finishing techniques, and you can get down to 1 micron surface finishes using different techniques there. And on surface treatments, you know, this is kind of a different one. So if you need to have decorative parts, we've actually did film transfer graphics onto different composite parts that happen to be for a yacht that you see on the left there, and then work with various types of, this is tiger coatings, powder coatings that we've done on the parts if you need a powder coating for whatever purpose. And then for the carbon materials, they are conductive, and we have metal plated with a nickel metal plating onto those parts, and that's what you see there. Just a couple more slides and then we can turn it over to questions. But what we really want to leave with all of you today particularly if all of you are working with additive processes. This is what we think that first of all, this carbon fiber sheet that I'm holding up, this has the printed image on it, similar to the drone that you see on the slide here. But you want to put as many parts onto that build sheet as possible, because the biggest cost of producing a composite part with this process is this carbon fiber sheet. Typically, it's about 60+% of the cost of the part. So you want to get as many parts onto that build layout. And oh, by the way, on that build layout, you can get the parts really close to one another, because we're heating and compressing this in a 50-ton heated press and applying uniform pressure and temperature across that surface area. We don't have to worry about warp and curl. So really loaded up with parts on there in order to be cost effective. And so kind of an example here is that this is a class 1 speed racer drone. We're doing drones for the military, and we're doing drones for commercial applications as we speak. This one was a 10-part assembly. All 10 parts was in that build layout that you see on the left there. It took about 150 carbon fiber sheets. It took 6 minutes to print those sheets. And then it took another 5.5 hours to heat, press, and remove the parts out of the build block. So you can basically make a complete drone every 5.5 hours. And what we've done there, because the printer is so fast, is that on the back end, you're probably thinking, well, gosh, that post-processing time is kind of the long pole in the tent. True. So what we've done is we've decoupled the heating from the pressing. And so what we've done is now set up a work cell far as the heating piece of it is decoupled the heating from the pressing. So you take your printed preforms in that's press jig, and you say you have like 5 different ovens, and we have the heating schedules for those ovens. And when they come out of the oven, then they get put into a press very quickly, and so that you can match kind of the throughput of your output on your printer by decoupling the heating and printing on that front. And last slide I had for all of you, and then we can turn it over to questions, is that, okay, kind of interesting. If this applies to you, happy to chat with you at future. I will be at the TRX in Golden, Colorado here in a couple weeks. So if you're going to be there, love to meet you and talk with you more if you would have interest. But this is a build layout of mechanical linkages. It's got 3 layers tall, and you can see it's really has a high density packing to it. 78 parts. It took 5 minutes to print all those 78 parts. Not 15 minutes, but 5 minutes to print that. But the important thing here is that if you came to Impossible Objects, we do provide part services, being a new technology right now. That part would cost you, for a fiberglass nylon 12 part, $7.44 if you bought it from Impossible Objects. That would be our sell price to you. But if you owned your own machine, and it depends on what type of amortization schedule you would have for your work cell, it'd probably be half that, as this kind of a make versus buy example for all of you. And oh, by the way, this is this is the same part in the build layout, but if you wanted to have kind of a mix of parts, you certainly could have that as well. And I think with that, that's what I had for all of you this morning.
All right, thanks, Jeff. Great presentation. We'll now head into the Q&A session. If you do have a question for Jeff and you haven't done so already, please go ahead and enter it into the chat. I know I have a couple of questions here that came in that I can get started with. So let's start here. So Jeff, how does the heating and pressing step keep up with the printed composite sheets?
Okay, well, that's a great question, and I'm going to go back to my earlier answer. It's originally, when we did this, we would put the printed sheets into a heated press. So you basically program the heated press based on the quantity of sheets and the height of that. And so we had the schedules and parameters. That's all developed there. But with the fast machines, it does not keep up because heated presses are very expensive CapEx equipment. Just for example, the size that you would need and the pressure and temperatures you need for this process would be about $150,000 for a heated press. But in order to maintain throughput, we said, okay, we have decoupled the heating from the pressing, and so what we do there is we have a number of lower cost, high temperature ovens. So the printed preforms go into an oven, and then they come out of an oven, and you have a bank of 5 or 6 ovens, for example. And you put your different printed that comes off the printers to keep up with the print. So you might need 6 ovens, but you might just need 1 press because the pressing time is fairly quick. And so that's how we're maintaining kind of that match of keeping up with the printer with the heating and pressing on the back end by decoupling the heating from the pressing.
All right, thank you for that. All right, let's go. Let's see. So we know with other processes, you're always going to have defects. So in the CBAM process, what happens if you do have a badly printed composite layer?
Great question. And this is one thing that we feel that, and our customers will be the judge of this in the future, by all means. But in order to minimize that from happening, keep in mind when we print a sheet, we have a vision system there. Did we print the complete image onto that fiber sheet? Yes or no? And we have a feedback loop there. And if it's no, because say a print head got clogged or we had a streak in it for whatever reason, we can purge that sheet and a couple sheets behind it and reprint. So that's one inspection step to prevent that from happening. The second inspection step is that when we actually go to apply flood coat that fiber sheet with a powder substrate, and then it sticks to the printed region, powder loading is absolutely another key factor in this process. We also have another inspection technique there as well, and kind of repeat that in situ loop there. And then lastly, if when we go to stack that, when you watch the machine running and you saw the sheets being stacked every 2.2 seconds, making sure we have proper edge alignment of all those sheets that's being stacked in that press jig, is that you don't have a sheet sticking out a little bit to the left or a little bit to the right, so that we can maintain material properties when we go to heat it and press it, and dimensional properties. So it's the in situ inspection is my long answer to that question.
All right, great, thank you. All right, let's see. I think we got maybe one more here. So how does the bead blasting removal process, does that have a chance of hurting the final part, maybe surface finish or quality?
Also another great question, very insightful question. And so the answer to that is no. And I don't know if your folks on the call here, but this is basically a part that's been partially removed from the build block. And you can kind of see these end corners here is the unfused fibers. These fiber diameters are about 8 microns in diameter. And I don't know if you can see it, but I can easily rip these fibers off. I'm making a mess on my laptop here, but and so we have the media used in the automated bead blasting system is a silica, a walnut shell. It's a blend, and it's a soft media that under pressure is just snapping these things off. As far as any surface finish of making any pitting in the surface finish or knocking off small feature details on composite parts, no. It's just enough to break the 8 micron fibers, and there's no ill effects to surface finish or small feature details on your composite parts.
All right, and then a follow-up to that, is it possible to use maybe different materials to get a different surface finish when doing the bead blasting?
Oh, as far as media?
Yes.
Yeah, yeah, you have. I mean, there's all kinds of media out there for grit blasting, and probably some of you might know that better than myself. But you don't want to get you don't get to get too. You want to pick a media that's like a metallic, because if you pick the wrong media, you will destroy your surface finish. So it's a balancing act there. So we have done some work with, what blends of media that you want to use. You certainly wouldn't want to use like steel or metal, because that would be not helpful. It would certainly remove the parts quicker, but it would also do damage to the parts. So media selection is absolutely key.
Okay. All right. So let's see. After heat treatment, how much volumetric shrinkage? Sorry, 1 second. How much volumetric shrink is observed, and then what is the density of the final part that's achieved?
Also, another insightful question. So it depends on the matrix material. I mean, obviously, there's differences between PEEK and nylon, and in general, it's around 1%. But we have offsets when we go to print that basically, depending on the matrix material that we have there, is applied to the model. We kind of scale it up to get to your final net shape. To give you kind of a general answer there. On fiber volume content, I'm going to give you a two-part answer. So on the non-woven surfacing veils with the random dispersion fibers, they run an X and Y. And that's where you're getting your strength property at, by the way, everybody. Compared to some of the other additive processes, it's the long fibers is where you're getting your strength properties from. On the non-woven fiber substrates, fiber volume content ranges from 20 to 50%. That's not, and it does not compare to anything far as structural in the aerospace industry. The two-part answer is now we're developing the unidirectional materials using a thermoset, not a thermoplastic. Fiber volume content on the unidirectional composite materials is close to 50%. And strength properties, is like 600 megapascals compared to close to 180 megapascals. So it's, over 3 times the strength property. Now, these unidirectional parts are now getting us into kind of what you might be seeing out of some traditional composite manufacturing, certainly for aerospace.
All right. So let's see. Back to the post-processing topic. Is it possible to use AMT vapor smoothing to post-process?
The answer to that is yes, but it's only going to be applicable to probably like the nylon materials. PEEK is typically very chemically resistant, and that's something we're looking at too. Is some of the AMT and other post-finishing techniques to see how we can continue to apply some of the other post-processing methodologies downstream for improved surface finish. But the general answer to that question is nylon, it would work. Don't think it would work for PEEK just because PEEK thermoplastics is chemical resistant.
Mm-hmm. All right. Thank you very much. All right. I think that's all the questions we got here. Thank you very much for those answers, Jeff. So let's see, make sure we don't have any more coming in. Doesn't look like it. All right. So I guess that's going to wrap up today's TRX webinar series. I would like to once again thank Jeff. Jeff, thank you very much for being a part of the TRX webinar series. Great presentation. And then if you have any further questions for Jeff, please reach out to him directly at jdegrange@impossible. I think that's a slash, or not slash, I'm sorry, impossible-objects.com. Thanks, Jeff. And then as a reminder, if you think that you or your organization will be interested in sharing on the TRX webinar series, please fill out the form on the website, or you can reach out to Zane Ross directly. Thanks, and everyone have a great day.
Thank you all. Appreciate it.
Thanks, Jeff. Bye.
Thanks everybody for coming on.